want us to take a look at another theorem here, and part of this comes out of that fundamental theorem of line integrals. It says that the line integral over C of f dr is path independent if and only if f is conservative. Now, path independent means this idea that it doesn't really matter how you get from the initial point to the terminal point. It just matters which point you start at and stop at. Essentially, you can take any smooth curve to get from the first point to the last point, and the line integral will still end up being the same, which is very interesting because if we remember the original definition of the line integral, it does require that we have that derivative of the parameterization of the curve in there. But if we remember back to the fundamental theorem of line integrals, we again didn't use that parameterization of r, we just used the potential function for capital F. Now, what we're going to do in this theorem that's a little bit different is rather than fully using the fundamental theorem of line integrals and finding the potential function, we still are going to compute a traditional line integral where we are going to use a parameterization of a curve, but we might not use the curve given. We might simplify the curve to something that's easier to work with because we're path independent, so it doesn't matter which curve we use. So let's take a look at that in this example down below. So we want to find the line integral of C of f dr. For f of xy is given there, it's y cubed plus 1, and then 3xy squared plus 1. And we're trying to do it along this semicircular arc from -1, 0 to 1, 0. Now we could compute this either in the traditional way of doing line integrals of vector fields, or we could use the fundamental theorem of line integrals. This one doesn't look, it doesn't look horrible to find the potential of, but we still might find it to be more work than necessary to find the potential function. What we're going to do is we're going to instead try and use this theorem. So first, let's still confirm that f is conservative. This part is still going to be necessary. So we're going to take that partial of m with respect to y, which is the partial with respect to y of y cubed plus 1, which will be 3y squared, and the 1 will go to 0. And then the partial of n with respect to x is the partial with respect to x of 3xy squared plus 1. So that first part, we'll take the coefficient on x, which is 3y squared, and then the 1, again, evaluates to 0. So this is conservative because these are equal. So conservative. So I want to go ahead then and use this theorem up above. So since it's conservative, this integral over C of f dr is path independent. So I'm not going to do the full fundamental theorem of line integrals where we find the potential function. I'm going to skip that part as well. Instead, we're going to use a different path. So we're just going to simplify this path up above, and we can choose how we want to do it, but ultimately we need to start at -1, 0 and end at 1, 0. And I'm just going to choose the simplest thing that I see, which would just be the straight line that goes from -1, 0 over to 1, 0. And where I'm going to parameterize this curve instead of the one up above. So the parameterization for this curve, well, we could just say let x be t, and then we could let y, notice y is actually just constantly 0 on this. And then we need to figure out, well, x actually needs to go from -1 to 1, so we should let t go from -1 to 1. So a very, very simple parameterization then. So then r of t is going to be t0. And then we're using Now we're going to do the definition of the line integral of this vector field, but we're just going to use this curve, this parameterization, instead of the above curve. It doesn't matter if I actually do that semicircle arc, I just have to get from -1, 0 over to 1, 0. So our prime of t is going to be 1, 0. So then down below, we end up with, we're going to do the line integral of c of f dr. We've got the line integral, we'd go over the values of t, so from -1 to 1. In f, we plug in that x of t and y of t, so we're going to end up with 0 cubed plus 1, which is just 1, and then 3xy squared, so 3t times 0 squared, plus 1, which will again just be 1. So we just have 1, 1, and then we dot that with r prime, which is 1, 0. So remember, this is f of x of t, y of t, and then we dot that with r prime of t. And we're taking this dt. So then this is the integral from -1 to 1 of just 1 on the inside, because we'd have 1 times 1 plus 1 times 0. So that's just going to equal t, and we evaluate it from -1 to 1, which means that I have 1 minus -1, which is 2. So this is another option. So one of the nice things here is I didn't have to find the potential function for f. So you sort of have a choice. Once you know that your function f is conservative, you can choose whether you think that it will be easier to find the potential function, or whether you think it will be easier to still compute it using the line integral definition, but by finding a simpler path to get from the initial point to the terminal point.